Welcome back, everyone, to another deep dive. Today, we're going to be looking at operating systems,
Ah, yes.
those things that make our computers actually work,
Right.
right? And we have some great material to guide us today.
Yes.
We have excerpts from two Italian computer science textbooks.
Right.
They're university level, so pretty advanced stuff.
Yes. These
They're,
are comprehensive sources.
yeah, it's a good blend of historical context, some conceptual explanations,
Yes.
even some practical coding examples in there, which is neat.
Absolutely. It's a very interesting mix.
Yeah, I think this will give us a real solid grasp of how these crucial pieces of software actually work.
That's the goal, to give everyone a peek behind the curtain, so to speak,
Exactly.
to understand the core functions of operating systems, from file management, memory,
Yeah,
all the way to handling processes and how they've evolved over time.
right.
It's a chance to really understand what's happening every time you use your computer.
So both of these textbooks start by taking us way back
Yeah.
to the very first computers.
Yeah, the early days.
I'm talking massive room-filling machines
Oh, yeah.
with no operating system
As we know it today, yeah.
as we know it.
Oh,
Can you even imagine that?
it's pretty amazing to think about.
Like, what did they even do?
Well, you have to remember these early computers were essentially giant calculators.
Oh, wow.
So operators, who were often the programmers as well,
Right.
would manually input instructions using switches and punch cards. Imagine that each program had to be loaded step by step.
Oh, my goodness.
A very painstaking process.
No wonder they were mainly used by scientists and mathematicians for complex calculations.
Exactly. They needed that computational power.
Right.
But even back then, there was this drive for efficiency.
Right.
And the textbooks mention this emergence of batch processing.
Yeah. Okay.
It was a revolutionary idea at the time.
What did that mean?
Instead of running one program at a time,
Right.
they would group similar tasks together
Oh.
and execute them sequentially.
Batch processing, I've heard of that, but mostly in the context of like old mainframe systems.
Oh,
you know?
yeah.
Is that you're saying that it's still relevant today?
Absolutely. Think about modern cloud computing platforms.
Okay.
They handle massive amounts of data, user requests.
Right.
They need to optimize resource utilization.
Okay. Yeah.
So they often employ batch processing techniques
Interesting.
to group and execute similar tasks, just like those early computers did.
So even in today's world of instant everything,
Right.
those early innovations still resonate.
They do. It's quite fascinating.
Yeah, that's a pretty neat connection.
It is.
But as computers evolved, so did operating systems. Right.
Of course, hand in hand.
What were some of the key milestones in that evolution?
Well, one of the biggest was the arrival of transistors,
Okay.
marking the second generation of computers, smaller, faster, more reliable.
Right.
And with that, new possibilities.
Okay.
Peripherals like printers, tape drives became more common, and new software tools like compilers and linkers emerged,
Okay.
streamlining program development.
Things were starting to get a bit more sophisticated.
Definitely, yeah.
Yeah.
And a key innovation during this period was offline processing,
Okay.
allowing input and output operations like reading or writing to those tape drives
Right.
to happen independently of the main processing unit.
So instead of everything grinding to a halt
Exactly.
while the computer waited for, a tape to load or something,
Right.
it could continue with other tasks.
Precisely.
Yeah. I can see how that would be a major improvement.
It was a significant step forward,
Right.
and this concept ultimately led to the development of overlapping I/O and CPU operations,
Okay.
which is essentially the foundation of modern multitasking.
Multitasking. Now, that's something we all use every day.
Oh, yeah.
I can't imagine life without being able to browse the web, listen to music, chat
Yeah.
with friends, all at the same time.
It's become essential, hasn't it? It really speaks to those early innovations that we take multitasking for granted today.
Right.
But let's dive a bit deeper
I did-
into what makes up a modern operating system.
All right, let's unpack this.
Yeah.
The textbooks talk about various components working together.
Uh-huh.
What are some of the key players, so to speak?
Well, one of the most essential is the file system.
Yeah.
Think of it as the librarian of your computer,
Okay.
organizing all your files and directories, making them easy to find and access.
So when I save a document, download a photo, the file system is what makes sure it gets stored properly,
Exactly.
and I can retrieve it later.
Precisely.
Okay.
And it's important to remember, a file isn't the data itself,
Right.
but a way for the operating system to represent and manage that data.
Okay.
It's a level of abstraction
Right.
that simplifies how we interact with information.
That makes sense. So the file system keeps things organized.
It does.
What about security?
Ah, yes.
I know operating systems play a big role in protecting our data.
Absolutely. Security is paramount,
Right.
especially in today's interconnected world.
Right.
Operating systems have built-in mechanisms to control access to resources.
Okay.
This includes everything from user accounts and passwords
Right.
to permissions that determine who can read, write, or execute files.
It's like having a digital security guard.
It is constantly monitoring and protecting our systems.
Right.
And then we have networking,
Okay.
which allows communication between computers.
Right.
This is the foundation of the internet.
Yeah.
Allows us to connect with others, access information, share resources across vast distances.
So every time I send an email, browse a website,
Mm-hmm.
it's the operating system's networking capabilities that make it possible.
Exactly.
Okay.
And there are other essential components like the command interpreter.
Right.
Historically, the primary way users interacted with computers
Yeah.
and still used by power users today.
Right. Right.
And then we have system programs.
Okay.
Think of them as built-in tools that let you manipulate files, get system information, even write your own programs.
Right.
So it's a whole suite of tools available.
It sounds like a lot of moving parts working together to make the magic happen.
It is a complex ecosystem.
Yeah. But how is all of this structured? How do these components actually interact?
Well, the textbooks describe operating systems as layered systems.
Okay.
Imagine a cake with different layers,
Okay.
each serving a specific purpose, but working together to create a delicious whole.
I like where this is going. So each layer in an operating system builds upon the one below it.
Exactly. They depend on each other.
Yeah.
The textbooks offer a simplified example with 5 layers,
Okay.
starting with user programs at the top,
Right.
followed by I/O management, console device drivers,
Okay.
memory management, CPU scheduling, and finally the hardware at the bottom.
So if I open a document in a word processor, that request travels down through these layers, each one handling a specific aspect of the operation.
Precisely. So the I/O management layer handles the interaction with the storage device.
Right.
Memory management makes sure there's enough memory available.
Right.
The CPU scheduler allocates processing time,
Okay.
and so on.
That's a really clear way to visualize how it all fits together.
It's a helpful model.
Yeah. But the textbooks also mention something called a microkernel.
Yes, an alternative design approach.
How does that differ from this layered approach?
Well, it's like taking some of those layers and moving them outside of the core operating system,
Okay.
running them as separate processes instead.
So it's a bit like outsourcing some tasks to specialized contractors
That's a good analogy.
instead of having everything handled by the main operating
Right,
system.
right. This approach can have benefits for both performance and security.
How so?
By keeping the core operating system smaller and more focused,
Right.
it can potentially run more efficiently
Okay.
and be less susceptible to attacks.
Oh, interesting.
It's all about trade-offs.
So it's a different way of organizing the work
Precisely.
with potential advantages depending on the requirements.
It depends on the specific needs and goals.
That's pretty clever.
It highlights the ingenuity of operating system designers,
Right.
finding innovative ways to manage complexity and optimize performance.
Right. But no matter the structure,
Yeah,
one of the most fundamental concepts, the idea of a process.
absolutely. The heart of the matter.
Okay, let's dive into that.
Right.
What exactly is a process in the context of operating systems?
Well, think of it like this. A process is basically an instance of a program in execution. It's like having a recipe of the program and then actually following the steps to cook a dish. That's the process.
Okay, so every time I open a new application or run a program, a new process is created.
Exactly. And each process has its own structure and life cycle.
Okay.
There's a process control block, or PCB,
Okay.
which acts like the process's ID card.
Great.
It contains essential information, like the process ID, its current state, and other control information.
So it's kind of like a digital fingerprint for each process,
Yeah, you could think of it that way.
allowing the operating system to track and manage it.
Yeah.
What about the actual program code and data? Where does that reside?
Well, the textbooks describe how a process resides in memory divided into different sections.
Okay.
The text section holds the program instructions.
Right.
The data section contains static data.
Okay.
And then there's the stack and the heap.
Okay. I remember those terms from my programming days.
Yeah.
The stack is used for function calls and local variables,
Right.
and the heap is for dynamic memory allocation.
Precisely.
Right.
And what's interesting is that the stack and heap can actually grow and shrink dynamically during execution.
So that must make things pretty tricky for the operating system to manage.
It does. It highlights the challenges of managing memory effectively,
Yeah.
making sure each process has the space it needs without interfering with others.
It's like a juggling act, trying to keep all those processes running smoothly without dropping any balls.
A very apt analogy.
So how does the operating system know which process to give attention to at any given time?
That's where the concept of process states and CPU scheduling comes in.
Okay.
A process can be in various states:
Okay.
new, running, waiting, or ready.
Can you walk us through those states? What does it mean for a process to be waiting versus ready, for example?
Sure. A new process is just that newly created.
Okay.
A running process is actively executing its instructions.
Right.
Now, if a process needs to wait for something,
Okay.
like data from the hard drive or input from the user,
Right.
it transitions to a waiting state.
Okay.
And once those resources are available, it moves to a ready state, basically queuing up for its turn to use the CPU.
So there's a whole line of processes waiting for their chance to run.
Yeah.
How does the operating system decide who gets to go next?
That's the role of the CPU scheduler.
Okay.
It uses algorithms to determine which process gets allocated CPU time and for how long.
Right.
There are different scheduling approaches. Some prioritize fairness, making sure all processes get a chance to run,
Right.
while others focus on efficiency,
Okay.
giving priority to processes that need immediate attention.
I can see how that gets pretty complex, especially when you have many processes competing for resources.
It's a delicate balancing act.
Yeah, the textbooks also mention something called context switching. What's that all about?
Context switching is essentially the process of saving the current state of a running process
Okay.
and loading the state of a different process that's about to run.
So it's like a super fast switcheroo,
Yes, very fast.
allowing the CPU to jump between different tasks without losing track of what's happening in each one.
Exactly. And this is happening all the time behind the scenes.
Wow.
So fast you don't even notice it.
That's pretty mind-blowing when you think about it.
It's a testament to the ingenuity of operating system design.
Right.
It's what enables seamless multitasking,
Right.
allowing you to switch between applications without interruption.
But what about processes working together? The textbooks talk about cooperating processes. What's the idea behind that?
Cooperating processes are processes that share data and work together to achieve a common goal. Think about a client-server interaction. Like when you browse a website,
Right.
your browser, the client sends a request to the web server,
Right.
which then sends back the requested data.
So those two processes, the client and the server, are cooperating to fulfill my request. What are the benefits of having processes cooperate?
There are several advantages. One is modularity.
Okay.
By breaking down a complex task into smaller cooperating processes,
Right.
you can simplify development and make the system more manageable.
Okay.
Another benefit is speed up. By running tasks concurrently, you can potentially reduce overall execution time.
Right. Makes sense.
And then there's information sharing, allowing processes to access and update shared data.
But if processes are cooperating in accessing shared data, wouldn't we need mechanisms to ensure they don't step on each other's toes?
You're absolutely right. That's where the concept of synchronization comes in.
Oh.
We need ways to coordinate the actions of cooperating processes
Right.
and prevent them from creating conflicts or inconsistencies.
So it's about making sure they play nice and share resources effectively.
Yeah.
What kind of mechanisms are we talking about?
Well, one fundamental synchronization tool is the mutex lock.
Okay.
Think of it as a special key that only one process can hold at a time.
Right.
If a process wants to access a shared resource, it needs to acquire the mutex lock first.
It's like a one-at-a-time sign on a shared bathroom, preventing awkward encounters.
Exactly. And once a process has acquired the mutex lock, no other process can access that shared resource until the lock is released.
So it's a way to guarantee exclusive access and prevent data corruption.
Precisely.
But what if we want more fine-grained control? What if multiple processes need to access a resource, but we want to limit the number of concurrent accesses?
That's where semaphores come in. Think of a semaphore as a bouncer at a nightclub controlling the number of people allowed inside.
So if the nightclub has a capacity of 100 people,
Right?
the semaphore would make sure no more than 100 processes can access the shared resource at the same time.
Precisely. A semaphore is essentially a counter
Okay.
that's initialized to a specific value representing the maximum number of concurrent accesses allowed.
Okay.
A process can perform two operations on a semaphore: wait and signal.
So wait would be like waiting in line outside the nightclub until someone exits.
Exactly.
And signal would be like the bouncer letting someone in from the queue.
Its semaphores provide a powerful mechanism for managing concurrency,
Yeah.
ensuring that shared resources are accessed in a safe and orderly manner, preventing those digital nightclub brawls.
This all makes a lot of sense, but I imagine that even with these synchronization mechanisms, things can still go wrong.
They can.
What happens if processes get stuck in a deadlock?
Deadlock is a classic problem in operating systems.
What does that mean?
It occurs when two or more processes are blocked, each holding a resource that another process needs.
It's like a traffic jam where everyone is stuck, unable to move forward because someone else is blocking their path.
A perfect analogy. Imagine two processes, Process A and Process B.
Okay.
Process A has acquired resource X and needs resource Y, while Process B has acquired resource Y and needs resource X.
Right.
Neither process can proceed, resulting in a deadlock.
So how do operating systems deal with these deadlocks? Do they just let everything grind to a halt?
Well, that wouldn't be very useful, would it?
No.
There are several strategies for dealing with deadlocks.
Okay.
One approach is deadlock prevention, which aims to design systems in a way that makes deadlocks impossible.
So it's like designing roads with overpasses and underpasses to prevent traffic intersections and potential gridlock.
That's a great analogy. Another approach is deadlock avoidance.
Okay.
This involves carefully analyzing resource requests
Right.
to anticipate potential deadlocks and prevent them from occurring.
So it's like having traffic lights and traffic flow management systems to regulate the movement of vehicles and prevent congestion.
Exactly, and if all else fails, there's deadlock detection and recovery.
Okay.
This involves monitoring the system for deadlocks and taking action to break them if they occur.
So it's like having tow trucks to clear accidents and get traffic flowing again.
Precisely, deadlock management is crucial for ensuring that systems operate smoothly and efficiently, even when multiple processes are competing for shared resources.
It's fascinating how operating systems deal with these challenges behind the scenes. But shifting gears a bit, these textbooks also mention virtual memory. What is that all about?
Well, virtual memory is it's a really clever trick
Okay.
that operating systems use to make your computer think it has more memory than it actually does.
So it's not like physically adding more RAM chips?
No, not at all. It's more about utilizing your hard drive
Okay.
as an extension of your RAM. Imagine your RAM as a busy kitchen countertop
All right.
and your hard drive as a spacious pantry.
I can picture that. How does this pantry become part of the countertop?
So virtual memory works by dividing a program's memory into these fixed-size pages. And the active pages are kept in RAM right there on the countertop,
Right.
while the less frequently used pages are stored on the hard drive over in the pantry.
Right.
And when a program needs a page that's not currently in RAM,
Okay.
it triggers something called a page fault.
Page fault sounds kind of bad.
It's not a disaster or anything.
Okay.
It's simply a signal to the operating system
Okay.
to go fetch the needed page from the hard drive
Right.
and load it into RAM.
So it's like realizing you need an ingredient from the pantry.
Exactly.
You got to take a quick trip to retrieve it.
And while fetching that page might take a bit longer
Right.
than accessing data directly from RAM,
Makes sense.
it allows your computer to run much larger programs
Okay.
and handle more data than would otherwise be possible.
So virtual memory is basically giving us the illusion of having more memory than we actually do.
That's a great way to put it.
That's pretty ingenious.
It is a clever solution.
But I imagine there are trade-offs, right?
Of course, there are trade-offs with everything.
Like,
Well, one potential downside is performance.
okay,
Accessing data from the hard drive is slower than accessing it from RAM.
right,
So if your system relies heavily on virtual memory,
right.
you might notice a performance hit.
It's like having to constantly run back and forth to the pantry.
Exactly. It slows things down.
Right.
That's why having enough RAM is still important.
Yeah,
But virtual memory is a valuable tool
yeah, sounds like it.
that allows us to push the limits of our hardware and run more demanding applications.
It's fascinating to see all these ways that operating systems are constantly working behind the scenes.
They are.
You know, optimizing performance, making the most of available resources. Speaking of optimization,
Yes.
the textbooks also dive into the topic of disk scheduling. Why is that so important?
Well, remember that unlike RAM, which is electronic hard drives, are mechanical devices.
Right.
Accessing data involves physically moving a read-write head across a spinning disk platter.
So it's not instant access like with RAM?
Right, there's this physical delay involved.
Well,
And that's where disk scheduling comes in.
okay.
The operating system has to figure out the most efficient way to service these disk requests.
Right, to kind of minimize all that movement.
Exactly, minimizing those physical movements and reducing delays.
So it's like finding the shortest route for a delivery truck to make multiple stops.
I like that analogy.
Minimize travel time and fuel consumption.
Precisely. And there are various disk scheduling algorithms,
Okay.
each with its own approach to optimizing that head movement.
So what are some of those algorithms?
Well, one simple approach is first come, first served, or FCFS,
Okay.
where requests are processed in the order they arrive.
Seems fair, but I guess not always the most efficient.
Exactly, especially if requests are scattered all over the disk.
Oh, yeah. Makes sense.
That's where algorithms like shortest seek time first, or SSTF, come in.
Okay.
SSTF prioritizes requests that are closest to the current head position, minimizing back and forth movement.
So it's like picking up groceries from stores that are along your route.
Exactly, instead of driving all over town. And then there's SCAN, also known as the elevator algorithm,
Okay.
which moves the head back and forth across the disk servicing requests along the way.
Like an elevator making stops at different floors, picking up and dropping off passengers as it goes.
That's the idea. These algorithms highlight how operating systems try to balance efficiency with fairness,
Okay.
ensuring that all requests are serviced in a timely manner while minimizing those wasted movements.
It's amazing how much thought goes into something as seemingly simple as reading data from a hard drive.
It's a complex task with a lot of factors to consider.
Well, we've covered a lot of ground in this deep dive.
We have
From the history of operating systems
this whole journey.
to their really complex inner workings. What are some key takeaways you want our listeners to remember?
I think it's important to appreciate the intricate dance of processes, memory management, file systems,
Right.
and all the other components that make up an operating system. It truly is a testament to human ingenuity.
It's something we often take for granted,
We do.
but it's what makes our digital lives possible.
Absolutely.
From multitasking to security to virtual memory operating systems are constantly working behind the scenes.
Right.
Managing resources, ensuring everything runs smoothly.
Silently keeping things running.
So the next time you open an application or browse the web,
Yeah.
take a moment to think about the amazing complexity and sophistication of the operating system.
It's worth appreciating.
That's making it all happen.
It is.
It's a world of invisible wonders. But hopefully with this deep dive, it's become a bit more visible and understandable.
That's our goal, to shed light on these hidden complexities.
Absolutely. And that's what the deep dive is all about, uncovering those hidden layers of knowledge
Peeling back the layers.
and making the complex comprehensible. We hope you enjoyed this exploration of operating systems.
I certainly did.
And we'll catch you next time for another deep dive into a fascinating topic.